Chapter 6 has a lot of similarities to Chapter 5 and also some differences. In this chapter, we're going to be dealing with what are called traveling salesman problems or touring problems, but in a lot of the same ways, we'll be using graphs and talking about circuits and paths. So let's get right into it. Let's start off with an example of what is a traveling salesman problem and what does it look like, just to sort of help us to distinguish these types of problems from those we would see in Chapter 5. So I'll go ahead and read this problem. It says a group of students located in Chicago is planning an eco-friendly vacation over winter break. They would like to visit St. Louis, Minneapolis, Cleveland, and they've decided they'll be biking the whole trip. So maybe that's not such a smart decision in winter, but let's just go ahead and believe that this fictional problem I made up makes sense. The order that they visit the cities does not matter, and they're wondering how many miles would it take them to do their vacation, basically to do each of these bike trips. And I'll go ahead and move my head because I'm in the way once again. Where we can, given this map, we can see what are the distances between each of the cities, and they're trying to optimize this trip so that they could bike it in the most efficient possible way. And this is kind of the thing that we're getting is there's actually a lot of different ways they could do this. Now, if they wanted to go to each of those cities in order, like if they had to go to St. Louis, Minneapolis, and Cleveland in that order, well, there's only one way of doing that trip. But if the order does not matter, there's actually a lot of different options that open up. And so, we have a lot of different things we can do. So, before we get into the math of these sorts of problems, we could kind of look at some of our options. So we're living in Chicago, so that's kind of where we're imagining starting our tour here. And if they were to go in exactly the order that was listed, it says, well, they want to go to St. Louis, they want to go to Minneapolis, they want to go to Cleveland, and then they want to go home to finish their vacation. And we could see, well, how many miles would that particular trip take by just adding up all of those numbers? And that would be one potential option. But as we can see, well, there's a lot of different routes. And this particular route used one of the, well, in this case, the longest leg on this entire journey, that between Cleveland and Minneapolis. And we could think about, well, what if they were to do a different route? Like, let's say they would, did this way instead. Could there be a more efficient possible route? And how do we go about finding those? And these are what we call traveling salesman problems. And so in the book, one of the examples they illustrate is a salesman who has to go to a bunch of different cities to do business, where basically each of the lines represents a set of costs to travel between different locations. And it's a different context, but that's kind of why they're called traveling salesman problems. But in each of the case, we're looking to go to each of the cities without, in an efficient manner by using the numbers on the graph. And so also notice that we're using graphs in the same way, using a series of dots and lines. Typically in this chapter, the lines don't represent streets like they did in the last chapter. They're representing like an entire length of travel between one point to another. So this could be a singular highway. Sorry, my mouse is not being shown. This could represent a singular highway, but more likely it represents a series of different connections which all add up to the entire goal, which is to get from one point to another in any way feasible or any way possible. Or in this chapter, sometimes we could imagine that we're flying between different cities and we want to do a vacation plan. Where each of the numbers, they could represent a distance like miles. It could represent a cost. Say, for example, this was the dollar amount that it costs to fly between the different cities, and we wanted to optimize how much money we're spending in this trip. Or it could represent time. A lot of times we might want to minimize the amount of time that we're spending on this trip. Now, these numbers wouldn't make sense for hours, but let's say in minutes, it took us that many minutes to travel from one city to the next. And we want to save as much time as possible traveling. So at any rate, notice that these graphs, we call them weighted graphs because not only are they graphs with dots and lines, and usually we label the vertices as I said in the last chapter, by, well, what is it? What is the location? In this case, we could label them with the whole city name, or you could say, well, CSM. Well, C wouldn't work because Cleveland and Chicago both start with C. But I think you catch my drift that we're labeling each of the vertices by location, but each of the lines also has a label which we often refer to the weight of the graph. So these are called weighted graphs, graphs that have numbers on them as well. Kind of like how a weighted voting system would be a system with a bunch of different players where each of the people had a number of votes. Here, we have all the lines and all the edges on our graph, but those edges have weights, and they have a unique weight depending on each edge. And the goal of these problems is to always visit each city once and return home. So basically, we're going to be forming a circuit. Like in this case, it was starting at Chicago and traveling to each other vertex and returning home. And you don't necessarily have to return to the start, but it's most typical in these problems. But the importance is the completeness in visiting all the cities. Kind of like on chapter 5, our goal was to visit every single edge on the graph in order to completely sweep the neighborhood. Here we're just trying to hit each vertex. And basically, in this term, the important term in this chapter is what we refer to as a Hamilton circuit or a Hamilton path, which is not to be confused with an Euler circuit and Euler path. So one thing that I think can help you with understanding the difference between Euler and Hamilton circuits is in chapter 5 we're focused on Euler circuits. We're focused on a complete sweep of the entire graph. In this chapter, we're not trying to hit every edge, right? The goal was not to bike every single line on this graph. The goal was to bike between each of the dots and return home in a minimalized fashion. And so our goal is to find what we call either a Hamilton path or a Hamilton circuit. And depending, in graph theory, a lot of times it's referred to as a Hamiltonian circuit or a Hamiltonian path, but our book uses the term just Hamilton. Obviously, it means the same thing, but if you look up these sources online or something, you'll see it referenced as Hamiltonian instead. I'm going to try to remember to call it Hamilton because that's what our book uses. And again, this is another type of thing in graph theory, like how an Euler circuit and Euler path, we have Hamilton circuits and Hamilton paths, where by definition it's a circuit that visits all of the vertices exactly once, as opposed to hitting all the edges. That's really the only difference between Hamilton and Euler. Euler hits all the edges, Hamilton circuit hits all the vertices. And actually, Hamilton circuits are much, much easier to figure out than Euler circuits because it has nothing to do with evenness and oddness. It just is all about hitting each location and returning back to the start. And typically, it's not that hard to find one example of a Hamilton circuit, but it raises a new complexity. It brings up a new issue in these problems as well. There's sometimes more than one different answer. Could be multiple different options for Hamilton circuits to solve, and we often want to focus on what is the best one. And so that's exactly what we're going to do in this chapter, is trying to find what we call an optimal Hamilton circuit by using various different methods of doing that. In a Hamilton path, typically we're not really too worried about those, but it's the same idea. It's instead of a circuit always starts and ends at the same point, whereas a path would start at one point and end at another point. And again, it would have to hit each vertex exactly once. And notice that in a Hamilton circuit, technically, since you're starting and ending at Chicago, you're sort of visiting it twice, but you're really only connected to each one once. So that the uniqueness still stands, even though if you were to write out this circuit using a letter write up like CSM, I'll use CL for Cleveland, C, so this is not good because I have two C's. So CH is Chicago, CL is Cleveland. This is horrible, but as I said before, we often if we were to do this as let's call them A, B, C, D, it would be A, B, C, D, A. And because it's a circuit, it starts and ends at the same point. Anyways, that gives us an example of this type of problem. And our goal in a traveling salesman problem is to always find an optimal Hamilton circuit, or to do it in a number of ways. And one of the difficulties with this chapter is that there's not always a definitive answer. Well, there is a definitive answer, but there's a lot of different ways that we're going to learn to go about finding them. So there's a few different algorithms, which are what each of the sections of the textbook focuses on. And what we're going to really focus on next is how do we actually find the answer? So there's what's called the nearest neighbor algorithm, the repetitive nearest neighbor algorithm, and the cheapest link algorithm. And we're going to practice learning how to find each of those. And each one of those finds good answers to this question: what is the best way of doing this? There's also what we call the brute force algorithm, which how I like to do it is I actually like to do 6.4 and 6.5 first, and then go back to 6.3 after, because brute force algorithm is very tedious and elaborate. Well, it's not elaborate; it's actually really simple, but it's kind of horrible to do. And we'll get, I kind of go out of order in this text in this chapter, as you'll see. But I think it makes sense the way I do it. Just so, anyways, we're going to come back to that one at the very end. But anyways, this is what we're going to be focusing on next. And also another thing about a way that a traveling salesman problem is often presented. Often you'll see a traveling salesman problem presented by using a table of data instead of a graph. Like here we have a graph to sort of visualize the situation, but you can also display that information in a tabular form as well. And in the next video, we'll look at drawing a graph and trying to envision the solution to a traveling salesman problem by translating a set of data to a graph.